Hello. In this lecture, we will start chapter 20 about AVL trees. And we will see AVL trees basically is also a binary tree. So in this chapter, we are going to discuss the concept of AVL tree and the techniques to balance a binary search tree and iterative implementation in the insertion for an AVL tree and recursive implementation for the insertion in an AVL tree and iterative implementation for the deletion in an AVL tree and recursive implementation for the deletion in an AVL tree. Okay, and we will also take a look at application driver for the AVL tree class. Okay, so the first section is about the AVL tree concept. Okay, and if you recall previously, in previous chapters, we learned the binary search tree. Okay, and an AVL tree is a balanced, and we call it a self-balanced binary search tree. Okay, so what does this balance mean? Okay, so it means that the balance is maintained so that the height difference between the two branches, so the left and the right subtree, does not exceed 1. Okay, the height difference, we also call it a balance factor. Okay, so the height. So what is a node's height? So node's height is the number of edges along the longest path from the node to a leaf node. Okay, and for root node, its height is also the tree height. Okay, so here is a key concept about the balance factor. Okay, so basically, an AVL tree is a binary search tree, but with balance factor. So it must cannot exceed 1. Okay, so basically it allows -1, 0, and 1. Okay, and let's take a look at the case. So the height during the balance factor basically is left subtree height minus right subtree height. Okay, so that's why we also have -1. Okay, so let's take a look, like for node B. Okay, in this case, so it doesn't have, for the left one, it doesn't have any subtree. Okay, doesn't have any edge. Okay, and the for the right it is 1. Okay, so this is 0, and the 0 minus 1, so that's why it's -1. Okay, and then for node F, okay, so its left subtree has 2 branches, 1 and 2, is it? So 1, 2, is it? So it's 2. The left subtree height is 2. And right doesn't have any branches, so it's 0. So that's why it's 2. Okay. Then let's see, node G. Node G, the left subtree, it has 1, 2, 3. So 1, 2, and 3. So the left subtree height is 3. And the right subtree, the longest one is 2. Okay, so 1, 2. So it's 2. Okay. And so uh, we have 3 minus 2, so it's -1. Okay, so that's node G. Okay, so this is the definition for AVL tree. So let's see, in this case, then we can see this is not a balanced binary search tree because node F, its balance factor is 2. Okay, so it's not a -1, 0, or 1, so it's already exceed 1. Okay, so this is not a balanced AVL tree, balanced binary search tree, so it is not an AVL tree. Okay, and so because of the definition for AVL tree is each node, its balance factor must be not exceed 1, is it? So for a binary tree, if we want it to become an AVL tree, we need to balance. Okay, the balance, so each node must be balanced. And how do we achieve it? Is that we calculate each node's balance factor, okay? And which is the height difference between the left and the right subtree, okay? So we must maintain that each node has the balance factor cannot exceed 1. Okay, so there's approaches to do the balance, and we will discuss it in later section. Okay, so for the previous uh, the binary search tree is not balanced, is it? But if we do some, if you recall, the node F is not balanced. But if we do some arrange it like this, then we can see each node, the balance factor meet the condition. So now it is a balanced BST tree, binary tree. So it is an AVL tree. Okay, so then the core concept for an AVL tree is it still binary tree, is that so it at most has 2 branches. So each node has at most 2 branches, okay? And the node need balance. So that's a new feature, okay, on top of binary tree, okay? So binary search tree. So node needed to balance. So the balance factor cannot exceed 1, okay? So is it still ordered? Yes. Okay, so it still meet the binary search tree. So left branch is less than the right branch. Okay, so that's for the order. So the operation it supports still support insert, delete, traverse. Okay, but we need a new operation, we call it a balance, to balance all of the nodes in the tree. Okay, and based on the concept of an AVL tree, so we can design it in Java as a genetic one. And because of the new requirement for balance factor, so for each bean node, okay, we have a new feature added, so the height. Okay, so for each node, we also need to know its height. Okay, the height is the longest path, is it, to the leaf node. And so for the constructor of this bin node, then we also, for the constructor with a parameter, then we also need one that also has a height. Okay. Everything else is the same as the previous binary search tree. And then for AVL tree, okay, and similar, it's generic, but because of comparison, so that's why we needed to support the generic must support comparable, okay. And that member the instance variable. So instance variable, no change. It's just a root node, okay? And then constructor, empty, and the height we also want to know, okay? The height of the tree. So it's a root node's height, okay? And as previous, we have search, insert, delete, okay? And those are in order, pre-order, and post-order for traversing, just like a binary search tree, okay? And we also, if you take a close look, you will see we also have a number of private methods, okay? So all of these are used for the AVL tree's balance purpose, okay? So the height of a node, this is height for a node, okay? And this is a node's balance factor, okay? And later on, we will do some operation so that we can convert an unbalanced binary search tree to an AVL tree, okay? Some operations, so we call it rotate right and rotate left around a node, okay? And we balance a node, okay? And we also needed to update the whole path, okay, from a node all the way to the root node. So the path is going to be recorded by an array list of the bin node. And so this is the update of the path height for each node. Okay, update the height of all nodes along a specified path. So the path is the path composed of the nodes. Okay, generally speaking, so from a node specified all the way to the root node. Okay, and the balance path. So you want to balance the node all the way to the root node from a specified, okay, and the path is recorded by a list of the bin node. And we also have a private method called get path, okay. So you specify a node and it's an array list. So the path return all the nodes along the path, okay? So from the root node all the way to the node. So that's the general operations about AVL tree, okay? The AVL tree definition, AVL tree class. Okay, and then next we discuss techniques to balance a node, okay? Balance node, individual node, okay? For a general tree, okay? Binary search tree. And there are different scenarios we need to consider, okay? The first case, we call it a heavy, so it's right heavy, okay? So it's right the case. So what does it mean? So this shows the keys. Okay, so it's right. What we can it's very obvious. We can see is that so node A is not balanced in this case. Okay, and it's balance factor is -2. Okay, so that means the right subtree's length is larger than the left subtree. Okay, and also its direct child, node B. Okay, its right branch is longer than its left branch in this case, okay, all equal. So that's the case for the right to right, okay. And for this case, so how do we balance it? Okay, we say we can do a left rotation to achieve the balance. Left rotation on node A. So what the left rotation means that you move we move node B up basically, okay, and then move node A down, okay. So make node A be the left subtree of node B, okay. And then we also make node B's subtree T2. So we first change node A's left subtree to T2. Okay, T2 is node B's subtree. And after that, okay, we make node A be node B's new left subtree. Okay, and make node A be left child of node B. Okay, then in this case, then we can see for all of the nodes, they are balanced. Okay, so this is right to right, so right heavy case. So then we make a left rotation for the unbalanced node. And the case 2, it's still right heavy, but it's right left case. So what is that? Okay, so this diagram shows, okay, so we can still see node A is unbalanced. Okay, its balance factor is -2, but this case is a little bit different from the last cases. For its right child, node B, okay, its left branch height is larger, is longer than the right one, okay. So then in this case, what we are going to do is we are going to bring its left node C up, okay, node C up, and then make node B its, so node C's right child, okay. At the same time, we also move node C's right child to node B's left child. Okay, so this is, so we first conduct right rotation not on the unbalanced node, but on the right child node of A. A is unbalanced, okay? So do the right rotation, okay? And after that, we can see this is still unbalanced, is it? But it's changed to case 1, to the previous case, is it? Okay, if it's changed to the previous case, if you recall, then we just need to do a left rotation for node A, is it? So what you can do is you put node, you move node C up, is it? And then, so what we do is we move node C up and make T2 be the right subtree of node A, okay? And then, so nothing changed from C to B, is it? So you just make a left turn for rotation for node A. Okay, so we first do a right rotation to get the case from case 2 to case 1. Okay, then apply the left rotation from case 1. Okay, then it's going to be balanced. So this is for right-left case. Okay, yeah, we already showed this. Okay, then case 3 is left heavy, but the first, for the left heavy, the first case is left. So similar as right, is it? So node A is unbalanced. Balance factor is 2. That means its left subtree's height is larger, okay, is deeper than the right subtree, okay, and also in this case, it's left child B left subtree's height is also deeper than its right subtree, okay. Then in this case, we just do a right rotation on node A, okay? So what we can do is, then what you do is you move, reconnect node A's right tree as node A's left tree, okay? And then you bring node B up, okay? So node B here and make node A be node B's right tree, okay? Then the tree is balanced, okay? Then it's an AVL tree again. So this is case 3, okay? So left. And let's see, the last case is still left heavy, okay? But this time it's left and then right. So what that means is the balance factor for node A is still 2, okay? But it's left child, node B, its right subtree is deeper than its left subtree. So in this case, then we first do a left rotation on node B, okay? And then we can convert the case to case 3. After we convert it to case 3, then we can just go ahead and do a right rotation on node A, like case 3. Okay, so it involves two rotation, okay, not just like the left, just one rotation. Okay, and then after the previous discussion, we know that for an AVL tree can be built from a binary search tree. That is, you just need to balance each node. Check if it's balanced. If it's not, then we need to do one of the above four balance techniques. Okay, so how do we? So when we have an AVL tree, okay, an AVL tree, and we will add some new node, do insertion, etc. And like over here discussed, before we add this, this tree is balanced. the AVL tree. Okay, we can see. So for node 55, its longest branch is 3. That 3, okay, and its right is 2, okay. So the balance factor is 1, okay. So it's balanced, okay, it's balanced. Okay, and then, and also for each node, node 50 is balanced, we can check, okay, each one of it is balanced. And after we insert 59, after we insert 59, then all of these parts not impacted. Okay, but when we do the insertion, so this is the path. Okay, we do for the insertion, is it? And after you insert a new node, then each node height change. Is it like node 57, then the balance factor is -1. And for 65, then it's 2, is it? And for node 5, then this is balance, it's 0, okay? So then we can see, okay, along the path, then node 65 is not a balance. So we need to do balance. Is it need to balance? So what is this case? Is it so this case is basically that left to right case. Okay. So it's a case 4. Is it? So with this case 4, then what we need to do is we first need to do the left rotation for the um, left chop 57, is it? So basically you move 59 up and then 57 here, is it? So now it's changed to the case of left. So that's case 3. Is it case 3? Then we need to do the right rotation on the node. Is it? So on the node, how do we do it? Yeah, then what we can do is we need to bring 59 up and then 65, is it? So here is that 57. So now this is balanced. And for node 55, okay. So this is longest path is 2, is at height, and this is 3. And node 55, then the balance factor is 1. So it's still balanced, and the whole tree is balanced. So now after you insert and do the balance, then we can see it's back to AVL tree again, okay? And so from what we just discussed, we can see after you insert a new node to an AVL tree, so along the path of the insertion for each node, you need to do the rebalance, okay? So that your tree can still be kept as an AVL tree. Okay, so this is an approach, we call it iterative implementation for the insertion. Okay. And similar for the deletion, okay, because for the major operation, okay, for an AVL tree is similar as a BST tree, that it's a search, insert, delete, and traversing, that, and because for search and traversing doesn't involve any new adding or removing a node, so the height of each node will not be impacted, so the tree balance will not be impacted. But for insertion and deletion, then it will impact the node's height. So it involves rebalance again, okay? So same thing after we delete a node. So the delete operation is exactly same as in binary search tree, okay? And then we need to update the height of all nodes along the path from the root node to the parent node. So keep this in mind, that's required, okay? And we need to rebalance each node along the path, okay? And the balance is performed bottom up, okay? So starting from the parent node and moving up to the root node, okay? So just like the insertion, so similar, okay? So you find the path and then you rebalance, okay? Like suppose we delete node 30 here, is it? We delete node 30, so you connect 28 with 35, is it? So after we delete it, then we start from parent node. So this is path to the to find the node, etc. So the path to its parent from the root node, then from bottom all the way up, we need to rebalance each of the node. Okay. So this is the discussion for the deletion, okay, iterative way. Okay, iterative way is after you do the deletion, then from the parent node, pass all the way back to the root node. Then we need to balance each node bottom up. And for the insertion and deletion in an AVL tree, we can also do the recursive implementation, okay? And we will take a look at it in our coding example. And the deletion, same thing, we can do the recursive way implementation. Okay, so that's a discussion about of the concept about AVL tree. And here is a national park, and you can see here it's a a large sand area. Okay, grand sand area. Okay, it's beautiful. Okay, and here is grand sand dune. Okay, and all of here dots basically are people. Okay, so it take quite efforts if you want to walk all the way up to the top of the sand dune. Okay, so that's the concept of the discussion for AVL tree. We will discuss the uh, coding in our next lecture. See you.